All right, so welcome to the first lecture on synchronization in coupled systems. So what do we want to do here? Let's start with a really easy example. So suppose I have an ODE, right? So x dot, and it's going to be a really easy ODE. It's just going to be linear and it's going to be on R, just R1. So of course we know exactly what's up with this ODE, right? So let's say that A is a real number, and let's say it's positive. Then what we know is that we just have a fixed point at 0. So if you're there, then your system just stays there. And we know that if you go slightly away on either side, if you're not exactly on this point 0, then you're going to move to the right or to the left. So you're going to move away from this fixed point, from this steady state point. As a matter of fact, we know exactly what the solutions are, right? This is all a very easy ODE. We know that the solutions are just given by x of t, right? So we're always looking for solution curves. X of t is just going to be equal to x0, whatever that was at the start. And then it's going to grow exponentially, right? So x0 is wherever you were when t is equal to 0. And then we know it's just going to be e to the power at. So this is just going to fly off to plus infinity or minus infinity, except of course when you're precisely at that origin. So we have a single fixed point and it's unstable. Now, what we're going to do with this easy ODE is we're going to get two copies of it. So you can think about this as having some kind of an object like a computer or a neuron in your brain, or maybe a species if you're doing a species competition. So we simply have a single node and it evolves according to our usual system. X dot is a of x. But I'm going to just very easily, very straightforward, I'm going to have two nodes. So that means I'll have two ODEs that are exactly the same, that are behaving exactly the same. So I'll also have, say, y dot for the second variable, the variable corresponding to this node. And it will evolve exactly the same. It will, of course, depend on its state. So I will just have y dot is a times y. So this system is just as easy as the previous one, right? So each of the components will respond, will act like this over here. So now we have a system on R2 and we have a single steady state point. And if you're slightly away from that, you shoot off to infinity. However, here's of course the main topic of the course. Now we're going to have these two nodes talk to each other. We're going to have them interact with each other. So we're going to have some kind of a coupling strength. So this will be alpha. This is some real number that dictates how strongly these two units talk to each other. And so it's going to be added to the formulas and it's going to denote interaction. So I have this alpha, and what I'm going to do is I'm going to give it diffusive coupling. So diffusive coupling means that you are talking to each other, but via the difference of the states. So here I'm going to take alpha times y minus x, right? So and here I'm going to take x minus y. So what's the interpretation of this again? Each node, so this was the node for x, and this is the node for y. Each node has its own dynamics. It is very straightforward. It behaves like this. And we're going to now make them talk to each other. So their states will also depend on the state of the other one. And like I said, more precisely, it will depend on the difference. So this is diffusive coupling. What we will see is that if you take alpha to be big enough, it aims to make this difference smaller. Now, one of the downsides of this system, so if we have alpha is equal to 0, so just the uncoupled system, is that everything flies off to infinity. So can we maybe change that? Can we maybe change that property by making them talk to each other? Now, one of the things that we have here is a very clear answer no, because even though we are on R2, right? So these are two systems, so we're now having a dynamical system on R2, there is an invariant space in here. And this invariant space is exactly given by the following line. And this is given by the state x equals y. So I can draw the line x equals y. And I claim that this linear space is flow invariant, meaning that when I start on there and I let my time flow, I will never jump off. So why is that? That's very easy to check. How do you check that this space is invariant for this system? You plug in x is equal to y, and you try to see if the equations for x are then also the same as the equations for y. Because if they're not, then you're going to walk off. But if they are, then you will always stay in this line. And indeed, if you plug in x equal to y, then you will just get exactly the same equation for both the x variable and the y variable, because this will be 0. So you will just get x is a times x. And similarly, of course, y is a times y. So that means that this coupling, this particular type of coupling, changes absolutely nothing about what's going on this invariant space. We call this, by the way, the invariant synchrony space. And it's called the synchrony space because on this space, x and y have the same value. So the dynamics of the x node and the y node are doing precisely the same thing over here. So, and moreover, like we saw, if indeed we restrict to this space, so only when we're on this space, the dynamics is the same as the original system we have. So the coupling is not seen even on this space, right? It's just the dynamics of one of the individual nodes. So in particular, if I'm on here, just like this system, I'm going to fly off to infinity, either to the right, so to the right upper corner, or to the left lower corner. I'm going to fly off. So I cannot fully stabilize the fixed point at 0 by taking this scheme, by making them talk to each other via some number alpha. But maybe I can do something better. Maybe I can arrange for the two nodes to start behaving the same. So this is the idea of synchronization. So even though we know that on here the nodes will just fly to infinity, maybe the difference between the nodes can be arranged to become very small. So what does it mean for the difference between two nodes to become small? It means that even though the nodes may start off doing very different things, eventually they will start doing the same thing, the exact same thing. And this is, of course, the idea of synchronization. So what we want to achieve is we want to build a system of, in our case, two very simple ODEs with with just behavior flying off to infinity. But we want to design this system, we want to couple them together in such a way that whatever happens, whatever the nodes are doing, they will start doing the same thing. So that means that you might start somewhere here, but as time goes on, you go towards closer and closer to this invariant line, this synchrony subspace. So, well, how can we do that? How can we analyze that? Well, starting at the system over here, maybe we can define a new variable that precisely encapsulates what we are interested in. So let's define a new variable. Let's call it z, and let's say this is precisely the difference between the two nodes, because that's exactly what we're interested in, right? We want to know. We're not so interested in what the nodes themselves are doing, but we want the difference between the two nodes to go to zero. We want it to go towards this synchrony subspace. So we're going to introduce this variable. And since both variables can be seen as the coordinates of some curves, some time parameterized curves that satisfy this ODE, the same holds for z. So I can just try to get the time derivative of z. Right? So what happens if I take the derivative of this difference? Well, it's going to be x dot minus y dot, right? Taking the time derivative of the sum of two functions is just the sum of the two time derivatives. So this just works well. And now we can plug in our favorite equations. So what do we get if we plug that in? So x dot, well, we have an equation for that. That's going to be ax. That is going to be ax plus alpha times y minus x. But y minus x, that's going to be minus z, right? So what I'm writing down here is just minus alpha times z. So this is just plugging it in for the x coordinate, for x dot, right? Just copying this. I also have to do this for y dot. So I'll get a minus, I'll get minus a times y, right? And here I have plus alpha x minus y. X minus y is z, right? That's our definition. We had a minus sign here, so I also get minus alpha times z. So putting that all together and noticing, of course, that multiplication by a is linear and x minus y, that was equal to z. So if I add all this together, what I find, hopefully, is that this is going to be a minus 2 alpha, right? A minus 2 alpha times z, right? Because this is a times x minus y, so I get a times z and minus 2 alpha z. So the ODE that I'm left with for z, and this is of course a bit unusual when you think about it, but it turns out that z satisfies an ODE that can completely be expressed in its own variable. And again, z is just the difference of the two coordinates, so z takes place on R. And it's a linear system. So there are only a couple of things that can happen. If this number, a minus 2 alpha, is negative, then we will have that the z variable just shrinks and gets closer and closer to zero. So this is when a minus 2 alpha is smaller than zero. So a has to be smaller than 2 alpha. So in other words, alpha has to be bigger than a half of a. So as soon as we make alpha this coupling strength, right? Remember, alpha was the coupling strength between x and y. If we make this bigger than the half of a, right? Than the half of this number over here, then we will just have that the z variables go to zero. And what does it mean when the z variables go to zero? That means that the difference between the states x and y goes to zero. So that means that we're indeed going to go closer and closer towards that synchronization manifold, that synchronization space. So in other words, the individual nodes themselves might be doing something strange. In this case, they will just be flying off to plus infinity or flying off to minus infinity. But the difference between their two states is going to go closer and closer to zero. So they will start doing the same thing. And of course, well, if A minus 2 alpha is precisely zero, then the z variable is stationary, but this is of course very degenerate. The chances are absolutely zero that if you do an experiment and you pick your alpha, that you picked it exactly equal to A. So this is a degenerate case. But of course, if we picked alpha such that A is still bigger than 2 alpha, right? So if alpha was instead smaller than A over 2, then the difference between the two nodes would also blow up in general. It would stay the same if the difference was exactly zero, but other than that, any difference between the two nodes would also explode. So what do we learn from this? So recall here, I just said I can rephrase this as alpha being bigger than A over 2 or alpha being smaller than A over 2. So if I couple the two systems together, like I did in this very easy linear system, of course, if I couple them together, then if my coupling strength is zero, then absolutely nothing happens. If my coupling strength is too small, so if it's smaller than A over 2, still not a lot will change, right? So we still see that variables that start off a little bit different will have these differences explode. They will become more and more different. But if I pick my alpha, my coupling strength between the two, to be bigger than this critical value, A over 2, then I all of a sudden start seeing that the two nodes start behaving exactly the same. We start to see this phenomenon called synchronization. And this is going to be the running theme of this class, this idea of synchronization. So I have systems, maybe easy systems for each of the nodes. They may have behavior that's not that interesting. In this case, everything goes to infinity, but it could have also been, of course, that it just all goes to some boring steady state point. But whatever the case may be, we couple them together in some kind of a network structure. So in this case, a very easy network, just two nodes that are communicating back and forth. But we couple them together, and all of a sudden you see interesting things happen. In this case, the two nodes start behaving the same. So this is, of course, a very easy example. It's all linear. So really, what did we do here in this example? We just looked at a linear system of the form x dot, y dot, right? So I'm just going to rewrite the equations over here. And this is going to be given, or this was given by a certain matrix because it's just a linear system. So this was the matrix A minus alpha. And here I have a coefficient minus alpha as well. Here I have minus alpha. And here I have A minus alpha again. So this was the matrix that we cooked up. That is the matrix that is describing this system. And of course, with x comma y applied to it. And this matrix is actually quite interesting, as we will later see, because you can write it as you can write it in a way that captures this network structure. So let me focus on this matrix again. So let me just write down that matrix without x and y. So that matrix is just given by A times the identity, right? Oh, I made a mistake here. I think this will be a plus, right? Because indeed we have A minus alpha x, but we have plus alpha y. This looks a whole lot better. These were, of course, pluses. So if I look at that matrix, I see that it's written by as A times the identity matrix, right? So this is just A's on the diagonal and nothing else. And this, of course, um, comes from the internal dynamics, right? So we say from the internal dynamics, if alpha is 0, we just had these two individual systems. They're not talking to each other. And this corresponded to the dynamical behavior of each of the nodes separately, which is why I say that this A identity part corresponds to the internal dynamics. And then I have an alpha here. I'm going to write it as minus alpha for reasons that will become apparent later on. And then what I'm putting here is I put a 1 here and a 1 here and a minus 1 here and a minus 1 here. Because remember, there's already a minus here. I wrote it like that. And this becomes a minus alpha, so that pans out. So this is really the linear system that I have over here, where essentially I've split the part that corresponds to the internal dynamics, right? So this is internal dynamics, and this is really signifying the network structure itself, right? So alpha was the coupling structure, was the coupling constant, the coupling strength, and this matrix 1 minus 1 minus 1 1 came from this part over here, right? This part over here, which ultimately corresponded, of course, to the coupling between the two matrices, between the two systems. And we call this matrix over here, we give it a name. It's usually going to be denoted by L, capital L, and it is called the Laplacian of the network structure. And what we will see throughout this course is that the Laplacian is the thing that's important. The Laplacian is the matrix that captures the network structure, and properties of L will have everything to do with how fast and how easy it is, therefore, to have two or more systems synchronize. Because what's going on with this matrix L, I can already give you a little bit of information about that. It has two eigenvalues. Now, one of the eigenvalues might be easy to see. One of the eigenvalues is just the number 0. And this corresponds to the constant factor, right? If I plug in 1, 1, I will see 0. And the other eigenvalue is the number 2. You can easily check this because it's a 2 by 2 matrix, but recall that the trace is going to be the sum of the eigenvalues. So you can also do it like that. And it corresponds to the eigenvalue 1, the eigenvector 1 minus 1. But why am I showing you this? Because this number over here was precisely the number that we saw over here. So the bigger this number is, if you have a more general matrix, and again, of course, I will tell you more about this, but the bigger this number is, the easier it is, the smaller we need to choose alpha, right? Because we said alpha has to be bigger than A divided by that number. So the bigger this other eigenvalue is, the easier it is to synchronize. In other words, the lower coupling strength we need to achieve synchronization. And that's going to be a running theme in this entire course, because what we will see next is that this value, we call this the Fiedler value of the Laplacian. This value, the Fiedler value, has everything to do with the connectivity of the graph, meaning that if a graph is less connected, this number will be smaller. So less connected, Fiedler value, or Fiedler eigenvalue, it's also called, is going to be smaller, which means synchronization is harder. If, on the other hand, your network is better connected, more well connected, then this number will be bigger. And that means that synchronization will be easier, right? Because then alpha only has to be bigger than A divided by a really big number. So remember, that's going to be the running theme. This Fiedler value, and of course, I'll tell you much more about this in a bit, but this Fiedler value is an indication of how well connected your graph is, how well connected your network is. And our intuition, of course, is that it's easier to synchronize a whole network when it's better connected, at least for these linear systems. And indeed, for these linear systems, that will turn out to be true. So that's what we'll talk about the next time.